Now let's talk about optimization. The concept of extreme values, maximum and minimum, are applied in solving optimization problems. In these problems, there are two equations involved: the optimization equation and the constraint. In solving optimization problems, the first thing to do is to determine what is to be optimized or maximized. Then determine the constraint. A constraint is a quantity that is true regardless of the solution. It can be viewed as a condition the problem must satisfy. In every problem, there is a fixed value which is a part of the constraint. Carefully analyze the constraint equation. Solve for one of its variables. The value of the variable can be used to replace the same variable appearing in the optimization equation. Simplify the optimization equation and find the first derivative. Next, find the critical values by setting the first derivative equal to 0. Test the critical values either by using first derivative test or the second derivative test. So let's have this example. The sum of two positive numbers is 12. Now what are these numbers if their product is a maximum? Alright, so let's highlight this part. So we are given the sum of two positive numbers is 12. So let's let x and y be the two positive numbers. Since we know here the sum of the two positive numbers is 12, then we can write x plus y equals 12. Now this equation is our constraint. Okay, that equation is the constraint. Right? Now, we also have here, okay, what are these numbers if their product is a maximum? So we have here, if their product is a maximum. So we can also write, or we can also let P to be equal to x times y. And that second equation is already our optimization equation. Okay, so next, solve for one of the variables in the constraint. So after we have identified all our two essential equations for this problem, then we will solve for one of the variables in the constraint. So here our constraint is x plus y equals 12. So let us solve for y. So we have here x plus y equals 12. Solving for y, we have y is equal to 12 minus x. Okay, so let's highlight that equation. And next, Substitute the value of the variable y in the optimization equation. Substitute the value of the variable y in the optimization equation. So our optimization equation is p equals x times y. So we have here p equals x times y. Substitute the value of the variable y in the optimization equation. So we have here p is equal to x times 12 minus x. Distribute x, so you have p is equal to 12x minus x squared. Now let's highlight that. Next step will be find or solve the first derivative of p equals 12x minus x squared. So find the first derivative of p equals 12x minus x squared. So we have here p prime is equal to 12 minus 2x. Next, set the first derivative equal to 0. Set the first derivative of p to 0. So we have here, okay, this one. Let's set that to 0. So we have 12 minus 2x equals 0. Negative 2x is equal to negative 12. Solving for x, we have here x is equal to 6. Let's highlight that. Okay, so we have there x is equal to 6. Now let's test. The first derivative of p, or the p prime, is equal to 12 minus 2x. Okay, that's what we have here. The second derivative, so that's just basically finding the derivative of our first derivative. So we have here that's equal to negative 2, so that is less than 0. So your second derivative is less than 0. So note that if the second derivative is greater than 0, then the function has a relative minimum at x equals c. Okay. Now, if the second derivative is less than 0, then the function has a relative maximum at x equals c. Alright? Now, since our second derivative is less than 0, then meaning to say our function has a relative maximum at x equals c. So the maximum value occurs when x is equal to 6. Okay, so now we can solve for the value of y. Solving for the value of y, we will go back, to our equation here. Y equals 12 minus x. So we will use this equation to solve for y. Alright, so solving for y, we have y is equal to 12 minus x. So y is equal to 12 minus the value of x, which is 6. So you have y is equal to 6. Okay, so let's highlight that also. So meaning to say, the two positive numbers are 6 and 6. That's it. Let's have now our second example. You are asked to fence a rectangular garden region for your vegetable garden and maximize the area using 260 meters fencing materials. What should be the dimension of your rectangular garden? Okay, so first thing, okay, we know here that what we have here is a rectangular garden. Okay, meaning to say, it will be better if we are going to visualize the garden. So let's have here, let's say that this is our rectangular garden. Let this side be x and then y, and of course this is x and this is y. There are two formulas that are needed to solve the problem. The formula for finding the area and the formula for finding the perimeter of a rectangle. As stated in the problem, the area must be maximized. Okay, they maximize the area, so the area must be maximized. So meaning to say, we will use the formula for the area as our optimization equation, and the formula for the perimeter, or the equation for the perimeter, is our constraint. Okay, so moving on, let's write our constraint. So let's let, okay, perimeter, so we have P, let's have P is equal to 2x plus 2y, because we know that perimeter is the total measure of all the sides of a polygon. So perimeter is equal to 2x plus 2y. And since we know here that we are using 260 meters of fencing materials, so that 260 meters is already our perimeter. So we will write 260 is equal to 2x plus 2y. And again, this equation that we have here is our constraint. Okay. Now let's have our optimization equation. Okay, so our optimization equation, in the problem, we are asked to maximize the area using to maximize the area. Okay, so since we used x and y as dimensions of our rectangular garden, so our area is equal to x times y. Okay, that's basically the formula for area, and that is our optimization equation. Right. So second step, we have to solve for a variable in our constraint. Now, this time we are still going to solve for y. So let's get the constraint. So we have here 260 equals 2x plus 2y. Solving for y, we have 260 minus 2x equals 2y. So we have here, okay, divide by 2. So you have here y is equal to 130 minus x. Let's highlight that. Okay, because we are going to use that later. Okay. Now, using our optimization equation, let us substitute the value of our variable y. So we have here A, or the area, is equal to x times y. Substitute the value of y that we have here. So we have area is equal to x times 130 minus x. Alright, you distribute. So you have area is equal to 130x minus x squared. Next, we have to find the first derivative of a equals 130x minus x squared. So we have here a prime is equal to 130 minus 2x. Right? Right? Now, next step, we have to set our first derivative to 0 and solve for the value of x. So we have here 130 minus 2x equals 0. So we have negative 2x is equal to negative 130. So x is equal to 65. Let's highlight this. Okay, so you have the value of x that is 65. Now let's test our first derivative of a, or our a prime is 130 minus 2x. So we have that here. Our a prime prime, or our second derivative, is equal to negative 2. And since negative 2 is less than 0, so meaning to say the maximum value occurs when x is equal to 65. So meaning to say we can solve now for y. We shall go back. Okay, we will use y equals 130 minus x, this equation, to solve for the value of y. So we have here y is equal to 130 minus x. So y is equal to 130 minus 65. Y is equal to 65. So let's highlight that. Meaning to say, the dimensions of our rectangular garden, the dimensions of the garden should be 65 meters by 65 meters. Meaning to say our garden is a square and a square is a rectangle. So that's it. Okay. So that's how to basically solve optimization problems. Now let's have example 3. A rectangular garden is to be fenced off along the side of a building. No fence is required along the side. There are 120 meters of fencing materials to be used. Find the dimensions of the garden with the largest area. So before we try solving the problem, then it's important that we know how to identify the important given in the problem. So we have here, we will have here a rectangular garden to be fenced off along a side of a building where no fence is required along that side of the building, and there are 120 meters of fencing materials to be used, and find the dimensions of the garden with the largest area. So similar with our problem number 2, or example number 2, we will need two formulas for this problem to be solved, we have the perimeter, and we will also make use of the area. Okay? Since we have here a hint that we have to find the dimensions of the garden with the largest area, so we know that our optimization equation will be the equation for the area of our rectangular garden. Okay? Now, before we start with our computations, let's draw first our supposedly garden. So our garden is rectangular and it's fenced off along the side of the building. So let's have this part as the building. So let's have this portion of our garden to be the building. And okay. Now remember, no fence is required along that side of the building. Okay, so to find the perimeter, then let's just have x on both sides and y for the width. So there. Now you may pause this video and try to solve this on your own and try to check if we were able to get the same answer. Okay, now let's continue. So as stated a while ago, we will make use of two formulas for this problem, the perimeter and the area. So we have here first the perimeter, so let's write the equation for the perimeter. So we have P, we have here 2x plus y. Okay, and since we have 120 meters of fencing materials to be used, so we know that 120 meters is already our perimeter. So we have here 120 is equal to 2x plus y. Okay, so let's highlight. And what do we call that equation? That is our constraint. Okay, and now let's write our optimization equation. So we have here, find the dimension of the garden with the largest area. So our optimization equation will be our equation for the area, and that is A is equal to x times y. So we have here x times y. Let's highlight. Okay, that is our optimization equation. Alright, next step is solve for the value of y using our constraint. So we have here 120 equals 2x plus y. So using our constraint, solving for y, so we have here 120 equals 2x plus y. So we have 120 minus 2x is equal to y. So let's just write it this way. Y is equal to 120 minus 2x. And highlight that equation because we are going to use that later. Okay, now next, after solving for y, let's now go back to our optimization equation. So we have here A is equal to x times y. Substitute the value of y that we have here. So A is equal to x times 120 minus 2x. So A is equal to 120x minus 2x squared. Alright, so let's highlight. Okay. If you are confused with the steps, you may go back to the first example, because I have written there the step-by-step procedure on how to answer this kind of problem. Okay, so okay, now continuing, we will use, or we will find the first derivative of a. So let's have here a prime, or just a set. We write a set so we will not be confused. So a is equal to 120x minus 2x squared. And then a prime is equal to 120 minus 4x. Okay, that is our first derivative. Next step will be, we have to set our first derivative to 0. So you have here 120 minus 4x equals 0. So solve for x. So you have negative 4x is equal to negative 120. X is equal to 30. So that is now our computed value for x. Next step, so we have to test our a prime, or our first derivative of a, is equal to 120 minus 4x. Our second derivative of a, or our a prime prime, is equal to negative 4. And since the second derivative is less than 0, then the maximum value occurs when x is equal to 30. Okay, so now we can solve for y. So in solving for y, we will use our equation that we had. Okay, we will use this equation. So you have y is equal to 120 minus 2x. So y is equal to 120 minus 2 times the value of x, that is 30. So you have y is equal to 120 minus 60. So y is equal to 60. So highlight the value of y, right? Meaning to say, the dimension of the garden is 30 meters by 60 meters. Okay, so that's all, and thank you for listening. I hope you learned something.